Hey, what's up everyone? So after the on-site interview with Pinterest, they actually reached out again for another architecture slash system design interview. This is the email I received from their recruiter. So it's pretty much saying that he received the positive signals from the algorithm slash data structure interviewers, but they needed a stronger or more signals from the architecture interview. It quite makes sense because the on-site interview was consisted of 3 algorithm interview rounds, but only 1 system design interview. It's a good thing. I get to show more of my system design skill. Or I'll simply disappoint them more. Let's see. The question was to design a system to detect similar products and provide better contents for users. You will go like, what do you mean by similar products and better contents? Those are two ambiguous terms, right? I believe they intentionally made the question ambiguous for the candidate to gather requirements and define scope by asking questions. So when I asked the interviewer the questions like, how to tell whether two products are similar or not, and what do you mean by better content? He gave me several examples and let me define what those are. So he gave me this example here, and he also gave me this example. Two shoes with the same price and the same color but different orientation. So after looking at several examples, I told him that we should look at the product holistically by comparing multiple attributes of the product. For example, its title, description, image, price, URL, and so on. And after we find similar products by comparing these attributes, we can provide better content to user by either removing duplicate contents, for example, if they're too similar, or combining them to provide better or richer information with less space. So once I understood the question better, I defined the functional requirements as follows. One is to detect products that are too similar, and second one is to provide non-duplicate or better contents to users. Then I asked more questions to understand how much data slash requests we're dealing with and some patterns that will be useful to design our system. For example, how many number of users we're dealing with, and database or storage size, and the ratio between read and write operation, and the volume of request. These are generally enough to get you started on high-level system design, but once you finish your initial design, you can dive deeper into different parts of the system and ask further questions. Now is the perfect time to pause the video and try to come up with your own system design. How would you design this? In this video, I'll explain how search query works in general and trade-off between offline versus online processes, and how to calculate similarity score offline and use the information to group similar products online. Before anything, we need to understand how the search query works. What happens when you type something like Nike shoes on the search bar and press search button or enter? How does Pinterest retrieve relevant search results for you? I'm pretty sure this is not the complete picture. I'm sure they will do different sort of optimization to reduce the latency and produce most relevant results for the user and for their business. However, this diagram should provide the general process of how the search query works, and it should be sufficient for the purpose of our system design. So when you click that search button, the query will first hit one of the load balancer. Then the load balancer will route the request to one of the backend instances. Then the backend instance would make a request to the search service. And this entire box is depicting how the search service works. I would like to describe the search service in 3 different steps. First one is the query understanding. Second one is search retrieval. And third one is search ranking. Let's start with the first step. This step involves query classification, query expansion, and entity extraction. Of course, there can be more. The purpose of this step is to understand better about the user query, extract as much information as possible, and polish the search term, for example, by correcting misspelled words before retrieving the search candidates on the next step. So let's see what I mean by that. So when you're searching for a new Nike shoes, for instance, called Air Zoom Alpha Fly, When you search this in Pinterest, you will not only get contents about these shoes, but you will also get other contents related to it. For instance, Alpha Zoom Pegasus, not sure if I pronounced it right, but Nike Men's Air Zoom Pegasus here, these. And also you might see some fashion related contents as well, such as this one. These contents are included because of the query understanding step. It categorizes your search term as fashion related, and it does query expansion based on your search term to include other relevant results. After extracting enough signals about the request, it moves on to the search retrieval phase. Pinterest contains billions and billions of pins. It's not possible to store all this information in a single machine, so the data is partitioned into multiple machines. During this step, it uses something called scatter and gather technique to retrieve the most relevant candidates. Let me explain what that means. There's an aggregator and leaves. Leaf is one that contains search indexes to retrieve contents from, and the aggregator here simply aggregates the responses from each leaf and return the results. You can also have here, like we only have a single aggregator, but you can also have multiple stages of aggregators depending on the size of your data and latency you want to have. For instance, if you want to return 100 results and let's say we have 10 leaves, each leaf would pick the top 10 most relevant contents to the aggregator, and the aggregator will aggregate them all, like responses from the leaf, and possibly sort them based on some quality score and send them to the downstream processes, which is the search ranking step. So once the retrieval is done, we might want to run a second round of ranking with some online data. You might ask, why do we need another round of ranking after we go through like billions of pins and reduce it down to 100 top candidates, 100 most relevant candidates, right? And the reason for this is because normally search indexes in the leaf do not contain online data. The data in search indexes are backfilled once a day or a few times a day in bulk in general. So if you want to use online data to rank the contents, for example, by looking at product availability and click-through rate, how likely is it for users to click the contents, we would need a separate step for that. So in this step, we would gather additional information about the 100 candidates we retrieved from the previous step and run it through some sort of machine learning model to rank them again. I hope you gained some general understanding about the search engine. Now, let's come back to designing a system to detect similar product. One approach is to compute the similarity score of search candidates during the request time. So after the search retrieval step, we can have another step that runs some sort of similarity detection algorithm and group similar products. So what kind of similarity detection algorithm we can use? So as a minimal viable product, we can start with using some sort of weighted average calculation, comparing multiple attributes of the products. So we can look into title, description, image, and price. And when we compare these fields or these attributes, we can give different weights depending on its importance. So we can say title comparison should weigh 20% of the comparison result, whereas image should weigh 50% of the comparison result. It's really similar to Elasticsearch, where when you do the ranking during the search, you can specify the title field should weigh 10 and description should weigh 5 here. Then these weights are kind of arbitrary. I just picked it randomly, but you can run some like different experiments, and we should be able to tune these parameters for optimal performance. Going forwards, long term, we can ideally build a machine learning model that performs better than this weighted average approach. But first, we should be able to prove that this aggregation feature helps the business and the users. It's not a good practice to build a complicated system, then later realize this feature doesn't work. Make sure you point this out during the system design interview because it's a really important point. So to give you a concrete example, let's say we have the following two blue shoes. Oops. So we've seen this example in the previous slide. we can say title and description matches 80% and 50% respectively. Then the images are 90% similar and the prices are the same. So going through the weighted average calculation, we'll get 80% confident that two products are similar. We can use the similarity score to either group the products or discard one of them before returning the result to the users. So what would be the downside of such approach that we just went over? Latency, right? Because you're doing more work when processing the request, it would definitely increase the overall response time. Before we had 3 steps, but now we have an additional step. And finding similarity between products is an expensive operation. You don't want to do everything online, especially when you can pre-compute some of the data offline. From the previous slide, we came up with the similarity score randomly, right? But you need to understand that coming up with the similarity score during the request time is an expensive operation. For the system design interview, we don't really need to know the algorithm that does the similarity comparison between the text or the image, but at least we need to understand that these operations are expensive and we should pre-compute some of the data offline instead of doing everything during the request time. So let's see what are some of the things we can do offline to improve our overall latency. We can pre-compute some of the data that will be used to determine similarity between products and make the periodic updates to the search indexes. So during the interview, I wasn't really sure what were the algorithm we could use to detect similarity, but the interviewer was not expecting me to know such algorithms. He just wanted me to explain the general process of finding similarity between products and what should be done, what operation should be done offline versus online. So the general flow is when the request comes in to create or edit a pin, it hits one of the load balancer first and be routed to one of the backend instances. First, it would try to persist the update in the database. Pinterest is using relational database to store pins, so these would be relational databases. Then before it returns the success response back to the user, it will publish new or updated pin for further processing in this message broker. We can use Kafka. And there will be external additional services that subscribes to this Kafka topic and process image or do further processing whenever there's an update. So one example is there can be an image processing services that further process the image, for example, resizing the image to decrease the overall size or improve the image quality in general. Then on top of that, it can also compute vectors that can be used to find similarity between other images, then store them back in the relational database here. And there can be other services that can compute other data that will be used to find similarity between products, right? So once those data are in, we can set up a periodic batch job that fetches new updates from this relational database instances and update the search indexes. So what I mean by the search indexes, it's these leaves here, where we gather relevant contents during the search phase. That's pretty much what I prepared today. If there are any other components you want me to discuss in the future videos, please comment below. Also, if you have any questions or suggestions to make on the design we just went over, please comment below as well. I would love to discuss on further improvement or alternatives.